Uniformly third order schemes for polygonal grids.
Thank you very much. I would like to thank the organizers for the invitation, and so far this program has been very interesting. So yes, so I would like to speak about polygonal grids, in particular icosahedron and cut cells, and the grids themselves have an order. It's an order of a grid, and of course that transfers to the order of the methods, and the methods I use on them, several come into questions. For example, which I use is local Galerkin, which makes it, I make the point, probably as convenient and local as for example discontinuous Galerkin, but it's all continuous. And all these methods have uniform high order. That means high order, I speak order 3, and I say in representation order. And uniform means that I don't leave any grid point out. Many problems I see in the literature with icosahedral grid, for example, can be traced back that for some points one thinks, oh, we do it less accurate. And that is very much a bad thing. So you should do all the same. And then I combined it with serendipity, which is the sparse grid, and I have some results as well. So this shows what a sparse grid is. It's actually this hexagonal grid. It's very sparse. So ignore all the other lines, but consider that points are only at the corners of the hexagon, and all the yellow points are unused, and the blue ones are shared between 3 hexagons, and the red ones are shared between 2. So you have more empty space than things, and this is for second order grid, and that actually means that you already for second order in 2 dimensions you have 9 grid points instead of 36. So it's worth about speaking on the saving, but I don't suggest it for the saving. I suggest that it's more accuracy. So if you have order 3 in 3D, the savings is actually quite big, is 12 to 81, and for the physics it is even more, 2 to 27 for the physics scheme. And you can project that you can simplify the time steps, which actually makes it quite economical. The point I want to make is that these high order schemes don't cost more than center difference, they cost less, because of the sparseness of the grid. Another application is these cut cells. So this is my cell, and I have grid points at the corners. I have unused grid points. This is actually the mountain which cuts something off of the cell, the mountains, and I have diagnostics points in here. This is how it should work, and the lines are here horizontal, the grid point lines, and that leads to more accuracy in the mountain representation. Actually, the applications I do are not all that fancy. For example, I don't do the sparse grid in hexagon, I do it on squares, where it's quite simple to perform. And the rule is, the more I go to real application, the more I use simplified schemes. For example, the cut cells I do only in second order. The polynomial order is a representation of a field inside a grid cell. And the amplitudes live here on the corners and then on the connection of 2 things. And if I aim triangular, then I have a dense grid. But if I use rhomboids, the grid is already sparse. So some saving associated, and already there a quite big saving can be done even on rhomboidal grids. So this is how the thing works. This is actually quite simple. You have an equation, and you define fluxes here and there, and that gives you a discretization of this example, for example. So that is quite easy. But now, how to go to high order? This is another simple example. So I define fluxes at these interfaces, at the uneven points. I just define them this way. They are not very good approximations of the real fluxes denoted by F. There are some fluxes defined in such a way that the derivative, that means the divergence, becomes very accurate. And here is when you put that into the flux equation, what comes out? It's the classical fourth order. Actually, I've thought about how to generalize this little concept, this easy concept. It can easily be generalized to hexagons and squares if they are regular. But for irregular grids, even in one dimension, it's a little bit more complicated. So here in one dimension, it's an irregular grid. So this is not like this. And these are the basis functions, the well-known head functions, and these bubble functions. And I use the discontinuous space, the same as used in discontinuous Galerkin. And these are the discontinuous basis functions. If I take two of these together, I get the continuous. I just have to require that the amplitudes are equal on right and left. So we have continuous nodes which never has to be adjusted, and we have the discontinuous nodes which have to be made continuous after one time step. And then the thing goes on. I have spaces. S is a continuous polynomial space which fits together continuous. Then I have the discontinuous space. Derivatives are always done in the function space without approximation, so they make the continuous function discontinuous. And the discontinuous, of course, has more than one amplitude at one point, a right and a left value. And in triangular grid, the main nodes have 6 amplitudes in the discontinuous space. And so the point is that I define these point fluxes to make this discontinuity again to a continuity. So that I do by operators. I use Galerkin, the differentiation, which is exact, and the regularization. Regularization actually is such that I work on the fluxes themselves and change them in such a way that the divergence is a continuous function. So I don't need to apply a Galerkin operator anymore. So with these operators, I can define standard Galerkin, which means time derivative is equal divergence, and to make the function continuous again, a Galerkin operator. And I use always this L Galerkin, local Galerkin, which is by nature fully local. The classical Galerkin involves a mass matrix, which is a non-local operation, which is somehow a pain in the neck if you want to use multiprocessor. So this is somehow very simple. And then I have projection chain. So I have also the collocation operator K, which actually, if I have a nonlinear function, takes this function at certain grid points and uses these to create the function space again. So if I start polynomial degree 3 and I have a square, like energy is a square of the basis functions, then I have 6-degree functions, but I don't want them. I take the grid points at certain points and create by them the third order interpolation. Again, it's actually all quite simple. So one of these schemes is more or less classical Galerkin if this is a classical Galerkin operator. So I do the from the fluxes Kg, I do the collocation operator, I do the divergence, I map by Galerkin, I use the local Galerkin into a space, and that is more or less, if that would be classical Galerkin, it would be the classical Galerkin scheme, but I use the local Galerkin. And you can have these two where I have another Galerkin operator in to create a conserving scheme, even if you don't have the conserving equation from the start with. I use simple O3, that is, I use the regularization operator and then apply it. So this is, I call simple O3, and then here I have some properties of these different methods. O101, that means an order 1 scheme on an order 1 grid. That is another name for center differences. On regular grid, you get a CFL number. I use always fourth order Rangakuta, and that is the same value to find in box. it is conserving, and irregular resolution is a bit difficult. Then I have classical O4. Its conserving is not known, but irregular resolution is actually difficult for this classical O4 scheme. But then I have order 2 standard. It gives 1.9, which fits well here in the increased order of approximation, takes away from the Courant number. But here, order 2 with order 4 differentiation, that is what I call the simple scheme. This for order 2 gives Courant number 4 against to this. So that is actually quite efficient. And the same thing, order 3, what I call simple, that gives nearly an CFL 4. That means the costs are such as if I would make my Rangakuta steps one after the other, so it's comparable to leapfrog in cost. And this is order 3 standard with the Galerkin operator. It's, of course, you lose against this from CFL. So there are economic options in it, but I don't suggest it as an option. An option to be simple. I suggest it to be more accurate. This is now this cut cell, actually not in high order and not on sparse grid. It's just on an Arakawa C grid, which comes out of the formalism as a special case. So this is actually the cut cell. So the idea is to treat the mountains more accurately. This is it shows only the vertical velocity, and it shows an analysis of the vertical velocity. How accurate and how we get to it, I probably can't discuss here. But let's assume this is the analysis of the vertical velocity. This is a forecast with a cut cell, and this is a forecast with the operational model of that time. You see that these structures here verify a little bit. So it's all kind, it's very bad. But in this case, they are superseded by very heavy noise. They are even there, but with too high amplitude. And that is the main difference between these. But there are even features which are very characteristic and known by many people who do climate integration over India. For example, here we have this high vertical velocity band right over the mountains. It shouldn't be there. For somehow physical more reasonable would be that it is here at the shoulder of the mountains. And another great difference is in China, where it is another color here. So these have impact on the rain. I don't show the rain because apparently our operational model had a problem with the rain, and but they have impact on the rain. And our new model, new climate model derived from this, has less problems. So what you can observe if you look at the rain, that these features here in amplitude become a little bit better, but in the vertical velocity not so much. But in these places, the shifting of this velocity band and the large scale difference over China translate into position differences of precipitation, and they remain even as compared to our current version of that model, which has better amplitudes and improvements which this model didn't have. So this shows that the impact on the forecast is quite big. This is actually the new cut cells, and this not, and this is the analysis. So this looks a little bit better, but it has great impact, this numerical procedure, on results. And I always show these. These are 50 cases, and we have done another 50 cases which show essentially the same. So unfortunately, only one-day forecasts. But in one-day forecasts, there is a really nice reduction of RMS against temperature and winds against radiosondes. So now I come to the horizontal part. So this is actually what I had for some time. Day 3 of Williamson test case 6. And you have to do, if you want to do convergence study and verification, not to integrate too long into time, because this case is eventually unstable. So in order to be predictable, you have to use small times, and I think it converges like third order, like it should be. This is a third order line, and it converges like third order, like it is constructed. And the accuracy, I think, is quite big. These are, I think, geopotential meters, so this is quite high accuracy. Actually, you can't produce this curve if you don't use double precision in the computer because the errors become rather low here. And so this I had for some time, and it's non-conserving. It's finite difference. It's classical fourth order adapted to the irregular grid on the icosahedron. So now with this business of the sparse grids, and I can make it conserving and on a sparse grid. I cannot show more than that it works. So I did not use this result was an icosahedron, but I didn't use the icosahedron. I used the cubed sphere for the simple reason that I wanted to use the software of home, and that uses this. But it's the same family. It's the same thing to my mind, the icosahedron and the cubed sphere. And with the help of Mark Taylor, I actually was able to do a sparse grid, and I can say no more than it seems to work. More I cannot say. We want to look more carefully in it. So this sparse grid with conservation and everything seems to be working, and that's all. Thank you very much.
So we have time for questions. Jürgen was too good with time. I have to be a tough chairman with time. Initially, you finished 3 minutes early, but better that than 3 minutes late, huh? So no questions.
Well, actually,
Yep.
so you showed comparison against radio sound observations, I think, several slides back, and you had a slight decrease in bias. Is that what those vertical profiles show?
Well, this was not bias. It was actually RMS which was reduced. The RMS was reduced here against radio sounds.
I see.
And I find this, I'm quite content with this because it's only one day. So what I really aim trying is to do the same thing in 5 days. When I think, I mean, one day the differences are necessarily very small.
So perhaps we'll thank Jürgen and move on to the next talk. Thanks very much.